In this section, we're going to take the next step and look at implementing recursive methods. So now that we've had this huge discussion of factorial, how we can write it as a recursive math formula, how it behaves if maybe it's not written properly, now we've done all that, let's try and take kind of a mile-high view of what recursion is. So imagine you're trying to compute the factorial of n, right? That's your full-size problem. Over here, right on my little diagram, that's being represented as this outer cloud here, the outer white one, right? And in here you see a function of n, right? So imagine that cloud represents your problem, and inside of that cloud is all the work that needs to be done, right? So in recursion, we say, okay, we have a size n problem, right? A full size problem. Because this is recursion, what we also say is that full size problem contains a subproblem. Or maybe if you want to be kind of technical, we'd say it's the n minus one size problem, right? It's a problem that looks the same as the bigger problem, right? That outside cloud, it looks the same as it, but it's slightly smaller or slightly simpler to solve. So you can think of this as remember we had the n minus one factorial, right? So our full problem in that previous section we talked about, our full size problem was factorial of n. Our sub problem, right, the recursive problem, was factorial of n minus one, right? A slightly simpler factorial. The key here is that inner problem, the sub problem, is exactly the same thing as my outer problem, right? It looks the same, right? It's still a factorial. Well, if that's the case, I can view that subproblem as having a sub-subproblem, right? So picture this inner white cloud now, right? The third one down, right? So my inner problem has another problem inside of it. And that repeats, right? It repeats recursively, right? It happens again and again and again, right? I have problems inside of problems inside of problems inside of problems. Well, at some point, I get down to something very simple, right? Essentially, it's n equal 1 or n equals 0, right? It's a problem that's very simple. It's a problem so simple that there's no subproblem inside of it. And instead, we can immediately figure out what the result is. For example, with factorial of 1 was simply 1, right? That's the base case, right? That's so simple that it's basically trivial, right? It's trivial. You could say, okay, the factorial of 1 is simply 1, right? I don't need to do any additional computational work. I can tell you what it is right now without having to look for another subproblem. This is kind of the basic recursive structure that we're looking for. So one thing you might be wondering is how do these problems relate to each other? Well, the idea is, if I want to compute the factorial of n, there's some way for me to do a little bit of work, right? And that little bit of work can be combined with the solution to the inner problem, right? So we said, that subproblem, right, the problem inside the full-size problem, that was n minus 1 factorial in the example earlier. Well, there's a way for me to, if I were to have the answer to that, there's a way that I can get from that to the size n problem, right, the full thing, by just doing a little bit of work. In our case, right, it was n times that subproblem, right, n times n minus 1 factorial. Right, so we do a little bit of work for the size n, and then we recursively combine that with the solution to the smaller problem, right? And then we do that again and again and again, right? So each of these clouds, right, each of these little areas in here, right, you can maybe think that I'm doing a little bit of work, right? I'm multiplying first by 4, then I'm multiplying by 3, then I'm multiplying by 2, right? So there's always this little bit of work that's going on in each of ththese clouds and making them smaller each time, right? There's still cloud left over for a while, right? I still need to solve my subproblem for a while, but I do a little bit of work each time until I get down to the bottom, right? To the base case. It's trivial. I know what factorial of n1 is, and I can just return 1. So this is kind of our overview of a recursive algorithm or a recursive function, right? Problems inside of problems, they get simpler and simpler and simpler until they're obvious to solve. So let's take a look at kind of how this happens, right, in Java if we actually have a method. So if we have a method that's recursive, we call it a recursive method. That means that particular method calls itself, right? So if I have a method called A, somewhere in that method, it calls A again, right? It calls itself. Inside of that method, I need to have two parts. I need to have the base case, which is the factorial of 1 equal 1 part, right? The stopping place, and then the recursive case, right? That was the n factorial equals n times n minus 1 factorial, right? I need to have those two pieces, right? Where do I stop, and then how do I make my problem smaller, right? So two pieces inside of my method. Generally, it's going to look like an if statement and maybe an else branch. Well, typically an else branch. Generally speaking, this works exactly like any method calling any other method, right? So when you call a method, you set up some parameters. Maybe those parameters, you have to compute them, right? Whatever you're setting to that method. And then when you call that method, right, those parameters are copied into the scope of that method, right? So then that other method that's being called, right, the one that you just called, has new data to work with, right? So that's generally what happens when you have methods calling other methods. And it's the same thing if a method calls itself, right? It's going to apply the same process, right? It's going to run the same code, but the parameters are going to be slightly different, and so that method's going to do something slightly different because of that. And so you can imagine, you have A calling A, calling A, calling A, calling A, right? Until you get to that base case, at which point it's done, right? It's computed whatever it set out to compute, and then it'll return that value, right? And it'll return it and return it and return it, right? So you'll have kind of this a bunch of A's calling each other, and then one by one they'll kind of merge down, right, and give their answer to the method that originally called them. So that's generally how recursion will look in a Java method. And you'll see a nice image of this later. So let's take a look at some very simple code. We talked about factorial before. Well, what about the similar problem of summing up a bunch of numbers? So of summing all the numbers between 1 and n, right? So if we want to sum the number 5, here the example is, oh, well, that means you sum up 1, 2, 3, 4, and 5, right? So sum of n equal 5 equals this. So here, if we want to use words, right, we say that, oh, the sum of 1 to n is n plus the sum of 1 to n minus 1. Let's actually try writing that kind of the same way we did factorial. It'll look a little bit different because I don't have kind of the exact same notation, but we can try. So let's say we have sum, right? So I'm going to start with my base case. Sum of 1 equal 1, right? So if I just want to take the sum of the bottom part, I just need to just return 1, right? I don't need to do any other work. And then over here, right, I have kind of my bigger case, my more general case. All right, okay, sum of n equals n plus sum of n minus 1. So this looks a little bit like our factorial. Again, the idea is we want to define something in terms of itself, right? If I want to find the sum to n, well, I can add n with the sum with a slightly smaller sum, right? 5 plus sum of 4 to 1, right, will give me the sum for 5. And this first rule here, right, I could actually write this a little bit different. So if I wanted to, right, I could actually write this first rule as being sum of 0 equals 0, right? That would give me effectively the same thing. Ultimately, it's kind of our decision based on what n is allowed to be, right? Do I let n go down to 0 or do I let it to be 1 or whatever, right? We want to make sure that our base case stops wherever our problem is supposed to stop. So that's our notation here. Let's kind of break out the more complicated stuff. So let's take a look at the math notation if we want to write this. So over here on the left side, we have the summation notation, right? So this is the notation we use in math, right, for taking the sum from 1 to n, right? We use the sigma to represent that we're taking a sum, and then at the bottom of the sigma, we have our variable that's going to be changing. So initially, I is equal to 1, so we start at 1. The 1 on top is how far we go, right? So we go up to n, and then each time, right, the things that we're summing up, right, the things that sigma is summing up, right, is going to be the variable I, right? So initially I is 1, so we add that then with kind of the sigma for I plus 1, right? We walk along one at a time, right, from 1 up to n, right? So from 1, 2, 3, 4, 5, right? That's what the sigma is giving us. So this is kind of basic math notation. Hopefully you've seen this before in another course. So let's say we tried to rewrite this. We wanted to maybe get rid of the sigma. So if we wanted to make this simpler, we could write this. This sigma, right, for this entire sum we want to compute is equal to n plus sigma of 1 to n minus 1, right? So you think of this as me doing a little bit of work here and then me having a sub-problem, right? I still need to have another sum, right? So I'm doing a little bit of work, but I still have a sum I need to compute, right? A sub-problem was inside of the full-size problem, right? This is the full-size problem, right? Let me say this is the n-size problem. This is the n minus 1 size problem, right? I know that it looks a lot like the numbers we're indicating up here, but really I just think this is the full-size problem, smaller problem. N being summed, right? That's the little bit of work I'm doing each time I have to do something recursively. And I can imagine, right, applying this again. And this is actually going to end up looking like the factorial example we did earlier. So this whole thing here equals n plus n minus 1 plus factorial. So this whole thing here equals n plus n minus 1 plus sum of 1 to n minus 2, right? So a little bit of work happening here, a little bit of work happening here, still have a sum at the end. And we can apply that again, right? Over here, we basically just have this. We have still the n and the n minus 1, right, for that previous time. Then we take out kind of another term, right? We compute a little bit more work, n minus 2 this time, plus the sum of 1 to n minus 3, right? So this is, again, a little bit simpler sum than we need to take at the end. And if you expand this all out, right, you get something like this, right? The sum of all those numbers, right, is going to be n plus n minus 1 plus n minus 2 plus n minus 3, and all the way down, right, until you get to the end, right, until you get to the plus 2, the plus 1. So this is kind of a symbolic expansion of what we talked about earlier, right? This is the process, right, that recursion works by. Is just we're doing a little bit of work each time, right? And you get a smaller problem, smaller problem, smaller problem until you get to the very end, and you don't need to do anything more complicated. You can just say, oh, the sum of up to 1, right, is simply 1. Let's go ahead and take a look at the actual Java code for implementing this. So over here we have a method called sum. Public int sum, one parameter, which is num. So this is computing, right, my sum from 1 all the way up to whatever num is. So let's go ahead and read through this. Initially we have int result, right? This is my first line here. So that's just going to be a temporary variable for me to store stuff. After that, I have this if condition, right? And this if condition is actually going to choose between looking at the base case or looking at the recursive step. So the first thing we're going to do, right, is we're going to check the recursive step, right? We want to make sure that we still have work to do, right? Or maybe we're already done. We want to check that. So first thing we do is we check to see whether num is equal to 1. Well, if num is equal to 1, then we're done, right? We know what the sum of all numbers up to 1 is, right? It's very simple. It's just going to be 1. So we set result equal to 1, right? And we're effectively done there, right? If this is an if statement, right, it's going to end up jumping down here to the return, right? So it's going to return that result as equal to 1. If it's not the base case, if it's some large number and we still need to do work, then it's going to go to the else branch. And the else branch is going to be a recursive step, right? So the else branch says, oh, the result of calling this method for that value of num, well, that's going to be the value of num plus the value of sum run on n minus 1, right? So notice that these two names here are the same, right? This is the recursion is going on here, right? We're calling ourselves. We're calling ourselves for a slightly smaller number, right? We said earlier, right, in the factorial example that we want to make sure that our n, right, is getting smaller each time so that we're getting down there, right? We're getting closer to our base case so that we can hope to finish at some point. So this is a very simple method, right? So this is a recursive way, right, to sum up all of the numbers, right, from n to 1. So a question you might ask yourself is, how does this actually look when it executes? Well, that's what we have on the next slide. So over here, imagine you're trying to run sum of 4, right? And you start here at the main method, right? Imagine you have a program, and the only thing it does is it prints out the value of sum of 4, right? That's all you're doing. So let's see how this would work, right? How it would be traced down. Well, initially, right, we would want to run sum of 4. Well, that's fine, right? That's our given, right? So imagine, right, we run the sum function. Well, inside that method, the first thing it's going to do is it's going to check to see whether that base case is met. Well, it hasn't because the parameter being passed in, num, right, that's going to initially be equal to 4, right? It's not 1 yet, so we're not done. So we're going to have to take the else branch. Well, the else branch, right, is going to be adding that 4 with sum of 3. Well, in that case, I need to run sum again, right? I need to do it recursively. So that's what this arrow here is representing, is that the call to sum of 4, right, generates this block here. It has to make a call to sum of 3, right? A sum for a slightly smaller value. Sum of 3 has to do the same thing, right? Again, the base case isn't hit, so in order to compute its result, right, so it can return something, it has to figure out what is sum of 2, right? So over here, right, this is for sum of 3. Sum of 3 is going to be 3 plus sum of 2, right? So we have a little bit of work to do, so we got to run sum of 2. Sum of 2 over here is going to add 2 with sum of 1, right? So again, we didn't hit the base case, and so it's going to call sum of 1. Now over here at this last step, when we do sum of 1, well, that means that num is going to be equal to 1. If num is equal to 1, then that base case, that thing is going to be true. So instead of making another call to sum, right, instead of doing another arrow down here that goes somewhere else, we'll actually be able to stop, right? This method here is just going to return 1. And that's what we see over here, right? So this last method here, right, for computing sum of 1, doesn't have to make any more calls. It just returns 1. Well, in that case, we go back, we return to this call here, right? This call that was for sum of 2. Well, sum of 2, right, now it has kind of the result of that recursive call, right? So that method there, right, that method called there, it's able to add 2 with the result of sum of 1, right, which is just 1. So it's adding up 2 and 1, so it gets back 3. Now that can complete, and so it passes it back to sum of 3. So sum of 3 right now has a result from sum of 2. So now it can do this, its addition, right? So over here, right, we did this one, and then over here, right, for this one, we do this 3 plus sum of 2, right? We had our 3 that we want to add, and then we looked for the recursive call to sum of 2. That finally completed out, giving us, right, the value of 3. Now we can compute this, right? 3 plus 3. And so again, this one completes. Go back now to sum of 4, right? Sum of 4, while it was trying to add 4 with the recursive call to sum of 3, well, now I can see, right, that thing returns back, right, and gives me the result over here, right? This is giving me a 6, if I were kind of to annotate these things a little bit. So over here we get a 6, and it can kind of finally compute the result, right? So it gets back our 10. Basically, right, the flow is we go down, making a bunch of calls, make the problem smaller each time, and then once we're done, we've gone to the very, very bottom, right? Gone to the base case, when we don't need any more recursive calls. We just return that, and then we build back up, right? We build back up to get our final answer, right? We combine all these steps together at the very end. So down, then up, right? Calls, then let the calls finish out. So this is kind of how a lot of general recursion works, right? Recursion where you only have a method calling itself once. A method can actually call itself multiple times, or call even other methods, which makes it a little bit more complicated. But this is how it looks, right, if you have just one method calling itself again and again. So this slide is going to actually summarize some of the rules we talked about earlier. So these are the typical keywords you see with trying to make something recursive. So this is going to be for everything, right? Now we're taking another step. Right? We've already talked about the specific example of recursions. Talk about how do we do this normally. So there's two things we mainly need to worry about: progress and termination. So progress was earlier when we said, hey, I have a factorial, and this applies to sum as well. Every time I do something, right, I want to make my problem smaller, right? I want to have n minus 1. I don't want to just do n again, because then it just keeps on going and going and going, right? It doesn't stop. I need to have, I need to be making progress, right? I don't want to have, factorial 4 equal 4 times 4 times 4 times 4 times 4 factorial, right? I don't want to have that going on, right? I want to be making progress, right? I want to have 4 factorial equals 4 times 3 times 2 times 1, right? I want to be going down. So that's what we talked about earlier. The general term is progress. The second term that we're going to be looking for is this thing called termination, right? So we want to make sure that we're going towards some base case, right? Some place to stop. So progress, termination, if you don't have those, you're going to have a bad time. Some other kind of general rules. First thing is, don't change your problem, right? So here I have my clouds that I'm using to represent a problem. On that very first slide I did, I had a cloud instead of a cloud instead of a cloud. One thing you have to be careful of is that you don't change your problem, right? We need to always be doing the same thing, right? We can't all of a sudden change the type of problem we're solving, because then we can't call ourselves on it, right? If all of a sudden my problem changes from, I don't need to do a factorial, or I need to do a sum, right? Well, then I can't call that factorial method again, right? It's the subproblem is the wrong type, right? All my problems, right, starting at the full size and then subproblem, all those need to look the same, right? They need to be the same type of problem. That way I can use the same method to solve them. So this is just something to look out for, right? If we don't have this, then we're not going to be making progress. The other way we don't make progress is if things never change. So this is where I said, what happens if we had that factorial of 4 equals 4 times factorial of 4, right? Well, in that case, I have this infinite recursion, right, where I never have a smaller problem to solve, right? It's still the same size, right? So that's what I'm indicating here. I have a full-size cloud, there was a recursive call to it, have a slightly smaller problem inside, but then that slightly smaller problem, when I go to solve that one, it's the same thing inside of it, right? I don't get a smaller cloud, I get still the same size of problem. That's an issue, right? I need to make sure that I'm getting smaller problems each time, or I'm simply not going to make progress, right? I'm not going to get towards that base case, right? I'm not going to be able to terminate. I just get stuck there, and I get kind of the same thing going on. I get out what I put in. So both of these are ways you can mess up your recursion, so you want to keep this in mind when you start doing some general problem solving with this technique.